In 1965, Perkins Engines stood at the pinnacle of diesel engineering. Their 4203 and 6354 engines had earned legendary status across Britain's farms and construction sites. Massey Ferguson tractors hummed with Perkins power. JCB excavators carved through earth with Perkins reliability. The company's reputation was bulletproof, but success breeds ambition. And ambition, as we'll discover, can lead to disastrous consequences. The mid-1960s presented Perkins with an irresistible opportunity. Heavy trucks were getting heavier. Buses were carrying more passengers over longer routes. Industrial applications demanded more power from smaller packages. The market was screaming for a compact, high-output diesel engine that could deliver serious torque without the bulk of traditional straight-six designs. Perkins' answer was the V8.510, an 8.36-liter V8 diesel that promised to revolutionize everything they touched. On paper, it was magnificent. In reality, it became one of the most disappointing commercial engine launches in British diesel history. The 510 wasn't just another engine, it was Perkins' declaration of war against Gardner, Leyland, and every other manufacturer dominating the heavy-duty diesel market. Where competitors offered massive, heavy straight-six engines, Perkins would deliver V8 sophistication. Where others struggled with packaging constraints, the 510's compact design would slip into chassis that couldn't accommodate traditional power plants. The specifications were genuinely impressive. Commercial Motors' August 1968 coverage detailed that the V8 510 was offered in two ratings: 150 bhp at 2,250 RPM with strong low-speed torque for buses, and 170 bhp at 2,800 RPM for coach and goods applications. The 90-degree V configuration kept the engine relatively compact, though in the Daimler Roadliner it was slightly longer than the Cummins V6 it replaced, requiring revised panel work around the rear floor. Dry cylinder sleeves improved block rigidity and reduced distortion, but unlike wet sleeves, they made servicing and replacement more complex. This tuning decision was intentional. The lower revving, high-torque output made the engine more responsive and flexible in congested urban traffic and stop-start intercity service. Testers praised the wide torque band, noting that it provided a 37% usable range and kept the vehicle pulling strongly, even in top gear at low speeds. The fuel consumption claims were equally bold. Perkins engineers promised specific fuel consumption figures that would make the 510 not just more powerful than competitors, but more economical too. Fleet operators, always mindful of running costs, were intrigued by the promise of improved fuel economy. Early adopters lined up immediately. Daimler offered the Perkins 510 in its new Roadliner SRP8 chassis, aimed at bus and coach operators. Independent bus operators, tired of Gardner's conservative power outputs, placed orders for chassis fitted with the revolutionary Perkins V8. Some agricultural contractors experimented with the 510 in heavy applications, though uptake remained limited due to emerging concerns over reliability. The engine's design philosophy reflected Perkins' confidence in their engineering prowess. Unlike American V8 diesels that prioritized brute strength over refinement, the 510 incorporated sophisticated features that demonstrated British engineering at its finest. The injection system used Sims pumps calibrated specifically for the V8's firing order. Cooling was handled by a carefully designed system that promised even temperature distribution across both cylinder banks. But perhaps most telling was Perkins' marketing strategy. They didn't position the 510 as an experimental engine or limited production specialty unit. This was their flagship, the engine that would carry Perkins into the 1970s and beyond. Perkins and Daimler promoted the 510 heavily for the Roadliner, positioning it as a modern alternative to the existing Cummins V6 option. The confidence wasn't entirely misplaced. Perkins had genuine expertise in diesel technology. Their smaller engines had proven themselves in millions of applications worldwide. The company's engineering team included some of Britain's most respected diesel specialists. If anyone could make a compact V8 diesel work, it should have been Perkins. Initial testing seemed to confirm their optimism. Prototype engines ran smoothly on test benches. Power curves looked excellent. On road tests in the Daimler Roadliner, commercial motor measured fuel consumption at 10 miles per gallon on a laden run. It passed its development milestones and moved into production with remarkable speed, perhaps too remarkable as events would prove. Perkins unveiled the 510 in 1965, and in 1968 it was being offered in the Roadliner and entering service with operators. From there, operators began fitting the 510 into new bus chassis, while agricultural contractors bolted them into heavy machinery, and industrial users integrated them into generators and pumping stations. For a brief, shining moment, it seemed Perkins had achieved the impossible: a compact V8 diesel that delivered on every promise. Then reality struck. The first warning signs appeared within only months of the 510's commercial launch, but they were subtle enough to dismiss as isolated incidents. A bus operator in Manchester reported unusual temperature readings on one cylinder bank. An agricultural contractor in Yorkshire mentioned rough running under heavy load. A generator manufacturer noted higher than expected maintenance requirements. Individually, these reports might have been attributed to installation issues, operator error, or simply bad luck. Collectively, they painted a disturbing picture that Perkins' service network was only beginning to understand. Bus operators and maintenance teams quickly discovered persistent overheating issues with the 510. Despite Perkins' advanced cooling system design, coolant flow was uneven between the two-cylinder banks. This led to one bank consistently running hotter, causing thermal stresses that often resulted in head gasket failures and costly engine repairs. The root cause was traced to the engine's internal coolant passages, which did not ensure equal cooling distribution, creating a negative feedback loop of increased temperature and mineral deposit formation. Operators in hotter climates, such as Australia, faced severe consequences, leading some transport companies to avoid the engine entirely due to the risk of catastrophic failures in remote areas where recovery would be prohibitively expensive. The cylinder sleeve failures proved even more catastrophic. Perkins initially built its reputation with engines employing wet cylinder sleeves, typical of early diesel designs. Over time, they transitioned to dry cylinder liners in their smaller 4- and 6-cylinder models to improve engine block strength and manufacturing consistency. However, this dry liner technology, while successful on smaller engines, posed new challenges when scaled up to the larger 510. Its larger size and operating conditions exposed unforeseen weaknesses. Industrial users of 510 power generators and pumping stations reported premature cracking and stress fractures in cylinder sleeves, even when maintenance protocols were meticulously followed. These failures compromised engine reliability and required expensive rebuilds. The combination of thermal stress, vibration, and less than optimal lubrication patterns in the V8 configuration challenged the integrity of the dry sleeve system, demonstrating that scaling up existing technologies without thorough redesign could lead to critical mechanical issues. The injection system problems added another layer of complexity to an already troubled power plant. The Sims injection system, while well calibrated for the engine's firing order, became increasingly erratic as broader mechanical issues, such as vibration from failing sleeves, compromised smooth operation. Operators noted erratic fuel delivery, engine surging under load, and excessive smoke emissions. Vibration was so severe in some cases that it loosened bolts and caused premature wear to tractor chassis components. Dealers often replaced multiple injection pumps in attempts to remedy issues, but without success. Eventually, some users reverted to more conventional engines like the Gardner 6LX, which offered more reliable performance and smoother operation under heavy agricultural workloads. The vibration issues weren't merely annoying, they were destructive. The 510's firing order, combined with its relatively short crankshaft and compact design, created harmonic frequencies that resonated through mounting systems and chassis components. Bus operators reported cracked dashboard panels, loose interior fittings, and premature wear of transmission components. Perhaps most damaging to Perkins' reputation was the growing perception that the engine failed to deliver promised power output. Dyno tests revealed that many engines produced significantly less than their rated 170 horsepower, particularly as mileage accumulated and internal problems developed. The power loss wasn't gradual, as expected with normal wear. It was sudden and dramatic, often coinciding with sleeve or head gasket failures. The pattern was becoming undeniable. Across multiple applications in different countries operated by various users with different maintenance standards, the V8.510 was failing in consistent, predictable ways. These weren't random mechanical failures or operator-induced problems. They were systematic design flaws that no amount of careful maintenance could prevent. By 1970, just 2 years after its triumphant launch, the 510 had earned a reputation that no manufacturer wants: unreliable, expensive to maintain, and prone to catastrophic failure. Bus operators began specifying alternative engines for new purchases. Agricultural contractors returned to proven straight-six designs. Industrial users sought more reliable power sources. The consistency of these failures raises uncomfortable questions about Perkins' development process and quality control procedures. How could an engine with such fundamental flaws make it through testing and into production? Were the problems truly unforeseeable, or were warning signs ignored in the rush to market? The 510's development stretched over several years, beginning in the early 1960s, though critics later argued that it still reached production before its problems had been resolved. As the story of the 510's failure unfolded, it became clear that the problems weren't a complete surprise to everyone. Later, technical analyses and reviews of the development process suggest that cooling system irregularities, sleeve stress patterns, and injection system sensitivity were likely all noted during early bench and field trials. However, the immense commercial pressure to launch the engine meant that these early warnings were likely tragically overlooked or dismissed. So the engine proceeded to production on schedule. The pressure to launch may have been overwhelming. Perkins had invested heavily in 510 development, including new production tooling and marketing commitments. Competitors were advancing their own designs. Customer deposits had been collected. The company's expansion plans depended on the 510's success, but the most damning evidence came from Perkins' own response to the mounting problems. Rather than issuing technical bulletins, recall notices, or comprehensive fixes, the company seemed to retreat from the market. Production numbers, initially projected to reach thousands of units annually, remained stubbornly low. Marketing emphasis shifted back to proven 4- and 6-cylinder designs. But the truth was, the problems with the V8 program were no secret to everyone inside the company. According to internal accounts, engineers were pushing for more development time, but management was committed to a launch date that had become a matter of corporate pride. The internal thinking was that they could address the engine's teething problems in a revised Mark II version later. It was a disastrous gamble. By the time those fixes were ready, the damage was already done. Customers had lost all confidence, and the market had moved on, leaving the engine obsolete before it even had a chance to be fixed. The human cost of these decisions extended far beyond Perkins' corporate balance sheet. By the end of the 1960s, frustrated operators were publicly voicing their disappointment. Complaints in the trade press highlighted high repair costs, reliability issues, and unmet promises of economy. The 510's failure had broader implications for British diesel engineering. At a time when domestic manufacturers were competing against increasingly sophisticated American and European designs, the 510's problems reinforced perceptions of British unreliability. Potential export customers, already skeptical of British quality control, found their concerns validated. The engine's reputation in buses and trucks became so negative that even successful applications in stationary equipment and industry could not redeem it in the broader market. A few 510 engines, properly maintained and operated within conservative parameters, provided acceptable service. But these isolated successes were overwhelmed by the chorus of complaints from disappointed users. By the mid-70s, Perkins had effectively abandoned the 510 program. No significant updates were released. Production dwindled to a trickle, then stopped entirely. The company's marketing materials quietly dropped references to V8 technology, focusing instead on refined versions of their proven straight-six designs. The questions that emerged from the 510 debacle have never been satisfactorily answered. Did Perkins engineers recognize the fundamental design flaws before production began? Were management decisions influenced more by financial pressure than engineering integrity? Could the problems have been solved with more development time and resources? Contemporary industry observers noted the speed with which Perkins distanced themselves from the 510 program. Unlike other manufacturers who stood behind problematic products with extensive warranty support and engineering fixes, Perkins seemed eager to forget the engine ever existed. Its quiet withdrawal suggests Perkins concluded that fixing the issues would be too costly relative to potential sales. Rather than investing in comprehensive redesign, the company chose to cut their losses and retreat to familiar territory. This decision, while perhaps financially prudent, left hundreds of operators with problematic engines that couldn't be economically repaired or supported. Parts availability became increasingly problematic as Perkins focused resources on current products. Service support dwindled as technicians moved on to other assignments. The 510's legacy extends beyond its mechanical failures to questions of corporate responsibility and engineering ethics. When manufacturers rush products to market despite known problems, who bears the cost of that decision? How should companies balance competitive pressure against customer welfare? These questions became more relevant as the automotive industry evolved towards shorter development cycles and increased market pressure. The 510's failure provided an early warning of what could happen when business imperatives override engineering judgment. The few remaining examples serve as mechanical monuments to one of British diesel engineering's most spectacular failures, a reminder that reputation, once lost, is nearly impossible to recover.